Hello everyone, welcome to another short video on solving a LeetCode problem with APL. In this video we are going to solve problem 1720, Decode XORed array. So let's see what's our task, and let me open an interpreter for us to work with. Okay, so there is a hidden integer array that consists of some non-negative integers. It was encoded into another array with length 1 less than that, such that the ith elements of the encoded array is the result of applying XOR between two consecutive elements of the array. Okay. So if the original array is this, then the encoded is that. And how can you tell? Well, because 1 XOR 0 gives 1, then 0 XOR 2 gives 2, and 2 XOR 1 gives 3. So we are given the encoded array and the first element, and now we need to figure out what the original array was. Okay, we can do that. The only thing that we have to pay attention to is the fact that XOR is a really interesting function, even though we don't have it in... Oh, actually we kind of have it in APL. So let's take a look at the following. Let me show you something which is... So XOR, even though we don't have a built-in that is built, a primitive that is explicitly for that, what we can do is we can use the not equals to function. So let's pretend that this is the binary expansion of some number. So this number, let me call this A. So A is this number, and B is this number, and we get that result. Now the cool thing is that if we take that result, let's call it C. Let's say that the result is called C. Now if I do C XOR A, then I get B. And if I do C XOR B, then I get A. So undoing the XOR operation is actually applying XOR again. So all we need to do is take our array and our original number, build the binary expansions of all of those numbers, and then XOR everything. So how do we do that? Let's see. So these are the numbers we get. So this is the encoded, and it looks like this. And this is the first one. So this is the first, just a 4. Okay, so now what we can do is we can append both together so that this goes in there. Now we want the binary expansion of these, so what we do is we take the decode function, but we want it to do the opposite, so we invert it because we want the binary expansion of all these numbers. And now 4 is 1, 0, 0, so notice that the binary expansion is along the columns. 6 is 1, 1, 0, etc. And now what we want to do is apply, what do you call it? We want to apply our XOR function, so not equals, to each pair of columns. And so what we do is so we apply a reduction, but windowed with a window size of 2. So what we do is we essentially grab pairs of consecutive columns and apply XOR. So notice that these first two columns, 1, 0, 0, 1, 1, 1, when they are XORed, they give 0, 1, 0. 1, 1, 0 with the column 0, 1, 1 gives 1, 0, 0, etc. So this gives me the XOR results of consecutive columns. And now what we want to do is go back to decimal numbers. So now instead of using the inverse of decode, we just use decode. Yeah, so there's that. And let me just make sure that... Oh wait, the output isn't this. I was so... What am I doing wrong? Sorry about that. Yeah, right, it's not... Let's see if this is what I meant to do. No, it wasn't. Yeah, because this is not like that. 4204. Yeah, my bad. Yeah, okay, cool. So the problem was that I described the wrong thing. So we were grabbing pairs of columns when really what I need to do is use the successive values to encode the results. Yeah, exactly, because from this example we couldn't tell, or maybe you could tell, but I was 1 XOR 0. Yeah, so in this explanation I'm clearly a little bit confused with something, but we've reached our solution, so everything is fine. The only thing here that is noteworthy for those of you who are more comfortable around APL and these scan and these reductions. So yeah, I should definitely try and say this. So just remember that a reduction takes a bunch of things, puts the function kind of in between all of those things, and then applies it so that we get a single final result. But if we change this to a backslash, we get a scan, which gives us the partial results or the intermediate results. I like to think of these as the intermediate results. And when we did this with the not equals, then what we got was, can I get, yeah, so let's get both of these here so that we can talk about them. So what's going on here is that we create this binary expansion, right? And now we do the XOR scan. So we do the XOR of the first two columns, and we get this 1, 0, 0. Now the next step is taking this column and doing the XOR with the wait. Gosh, I'm so lost. How could I get the correct answer and not be able to explain what I did? Isn't this amazing? Oh, right, I'm being silly again. So sorry about that. So we do the scan. We start with the first column. So that's the first column. It stays the same. Now the second column is going to be the first XORed with the second, so it's that. Okay, now the third column is going to be this one. So the previous result XORed with the next one, which is 0, 0, 0. And then this fourth column is XORed with a 0, 0 to produce that one. And then the fifth column is XORed with the fourth of the result to produce that. So that's what happened. And now notice that this only happened like that because the XOR function is associative and commutative. It has all of these nice properties, and so the scan, it's behind the scenes, it's doing something that maybe is a little bit surprising to some of you, but it's this would have given essentially the wrong result if the XOR function were not associative and commutative. Yeah, and I know that I'm not sounding very smart, but you don't have to take my word for it. So you can, I don't know, let's do the following. Let's do a minus scan on 1, 2, 3, 4, just for good measure. And now what we have to notice is that the final result doesn't match the same description of the process I gave here, because minus is not commutative and associative. So the first element is just 1. Now the second element is going to be 1 minus 2, which is minus 1. But then the third element, the process I gave here, would be minus 1 minus 3, and that would give minus 4. But in fact, the third element is going to be this 1, 2, 3. So it's a minus reduction on the first three elements. And when we do a reduction in APL, what is happening is I'm inserting the functions in between the elements and executing this, but well, APL executes from right to left, so we first do 2 minus 3, which gives minus 1, and then we do 1 minus that, which gives 2. And that's why there's a 2 in there. Okay? And then it looks like it's a 2 minus 4, which gives minus 2, but that's not exactly what's going on, because the fourth element is going to be just a plus reduction on that. But this is the same as inserting minus in between all of these things. And what it does is, well, 3 minus 4 is minus 1. 2 minus minus 1 is 3. And then 1 minus 3 is minus 2. Okay, so that's what's happening. Yeah, but because the XOR function is associative and commutative, then everything is fine. Now I'm just not convinced that I got this right, because I think there was just a... Yeah, exactly. So now I do the scan and then I decode again. And I get the correct results. Yeah, right, because this is the first of the result. Yeah, of course. Yeah, so now this is fine. This is the actual solution. And is this tacit? Can we make this tacit automatically? Not really, but almost. Yeah, so let's just leave it at that then. Let's not make this even worse by embarrassing myself even further. So this is what we did. The solution is taking the first onto the all of the other things. I'm assuming that the first is the left argument, but it's, you can swap this around. Then we find binary expansions of things. Then we do the scan with the XOR function, and then we turn everything into a decimal number again. So first solve the encoded. Oops, I did something wrong again. Why is it that I keep making mistakes? Oh, it's because of stranding issues, and now I'm trying to make a screenshot. Yeah, so we need this to tell APL that the -1 and the alpha are not supposed to make a whole array together. So that's that, and then first solution and the encoded gives us that, and then the other test case was, the first was 1 and the encoded was 1, 2, 3, which should give 1, 0, 2, 1. Okay, so this is it for this solution. This was embarrassingly long, and I should have recorded, but I do want to make these videos as my first reaction to a specific problem, so it wouldn't be fair to you if you couldn't see myself get all confused. So yeah, do leave your alternative suggestions in the comments. Like, how would you solve this problem? Would you do the same thing? Would you do a different thing? And excuse me for all the confusion, and I will see you in the next video. Bye.